Welcome back for another deep dive. This time, we're going to crack open a textbook.
Oh, fun.
Yeah,
I love a good textbook.
it's called Statistical Inference,
Okay.
and we are going to dive deep into the world of probability.
Oh, probability. That's a good one. It's amazing how something like that,
Yeah.
it seems so abstract,
Yeah.
but it plays such a huge role in our lives, like,
Mm,
even if we don't always realize it.
yeah.
Even Sherlock Holmes,
Oh, yeah.
master of deduction.
He knew about probability.
He understood it.
Oh, I remember that quote from the Boscombe Valley Mystery
Oh, yeah.
when he says, "I find it hard enough to tackle facts, Holmes, without flying away after theories and fancies."
Oh, that's such a good
He's
one.
basically saying that understanding probability helps us make sense of things, even
Oh,
when they seem random or unpredictable.
exactly. And that's what we're going to be doing in this deep dive. We'll unravel the mysteries of probability, giving you the tools to think about uncertainty in a whole new way. We'll start with the foundations, using clear examples and relatable scenarios so you can follow along no matter your current level of expertise.
Okay, perfect. I'm ready to become a probability pro. So, where do we begin this mathematical adventure?
Well, any good adventure needs a solid starting point, right?
Right.
For us, that's set theory.
Okay.
Think of it as the language that we use to describe and manipulate probability.
Set theory. Okay. Is that where we get those Venn diagrams with the overlapping circles?
You got it. Venn diagrams are a great way to visualize sets
Yeah.
and their relationships. But before we get to the visuals, let's lay down some basic definitions.
All right.
First, we have the sample space,
Okay.
which is essentially a list of all possible outcomes in
Ah.
an experiment.
So, if we're flipping a coin, the sample space would be heads or tails.
Exactly. It encompasses every possible result of that coin flip. Now, imagine we're looking at something like SAT scores at a university.
Okay, then the sample space would be much bigger, right? It would include all possible scores from 400 to 1600.
You're catching on quickly.
Yeah.
The sample space is always tailored to the specific experiment or
Mhm.
scenario that we're analyzing. Now, within that sample space, we have events.
Okay, so an event could be something like scoring above 1400 on the SAT.
Precisely. Events are simply subsets of the sample
subset.
space. They represent specific outcomes or combinations of outcomes that we're interested in.
Okay, so we have our sample space, our universe of possibilities,
Yes.
and then we have events, the specific things we want to analyze.
Exactly. And set theory provides us with a set of tools
Right.
or operations
Okay.
to manipulate these events.
Okay.
We have unions, which combine events,
Okay.
intersections, which find the overlap between events and complements, which define what's outside of an event.
So if we have the event scoring above 1400 and the event scoring below 600, the intersection would be, well, nothing.
That's right.
You can't do both.
You've just stumbled upon the empty set,
Okay.
the set with no elements.
Right.
It might seem trivial, but it plays a crucial role in probability by representing impossible events.
Right, like finding a unicorn. Impossible. Wow.
Exactly. Now, these set operations might seem pretty basic, but they lay the foundation for everything we do in probability. They allow us to express complex events and relationships in a clear and concise way.
Okay, I'm starting to see how set theory provides the building blocks for understanding probability. It's like learning the alphabet before you can write a novel.
That's a great analogy.
Yeah.
And once we're comfortable with sets and their operations, we can move on to defining probability itself.
Okay, I'm ready to go from the alphabet to writing those probability sentences.
Before we jump into calculating probabilities,
Okay.
there are two important concepts we need to understand.
Okay.
First, we have disjoint events, also known as mutually exclusive events. These are events that cannot happen at the same time.
So, like getting heads and tails on the same coin flip, those can't both happen simultaneously.
You've got it. Disjoint events have no overlap in the sample space. The second concept is partitions.
Okay.
A partition divides the entire sample space into non-overlapping events,
Oh.
ensuring that one and only one of those events must occur.
Okay, so if we think back to SAT scores, we could partition the sample space into events like scoring below 600, scoring between 600 and 800, and so on, all the way up to scoring above 1600.
Exactly. Each score falls into one and only one of those categories.
Mhm.
That's a perfect example of a partition. Now, with these concepts in our toolkit, we're ready to talk about how we actually assign probabilities to events.
All right, let's get down to the numbers. How do we determine those all-important probabilities?
There are two main ways to think about probability: the frequency interpretation
Okay.
and the axiomatic approach. The frequency interpretation is what most people intuitively understand as probability. It's based on the idea that if you repeat an experiment many, many times, the proportion of times an event occurs will approach its true probability.
So if we flip a coin 1,000 times, we'd expect to get heads roughly 500 times.
Precisely. The frequency interpretation is all about long-run averages. But the psi approach has its limitations. It relies on being able to repeat an experiment, which isn't always possible. That's where the axiomatic approach comes in.
Okay, axiomatic approach sounds a bit more formal.
It is. The axiomatic approach provides a more rigorous mathematical foundation for probability. It starts with a set of fundamental rules or axioms and builds from there. These axioms ensure that our probabilities are consistent and make sense.
So what are these magical axioms?
They're called Kolmogorov's axioms, named after the brilliant mathematician who formulated them.
Got it.
The first axiom states that the probability of any event is always between 0 and 1.
That makes sense. An event can't be less than 0% likely, and it can't be more than 100% likely.
Right.
What about the other axioms?
The second axiom says that the probability of the entire sample space is always 1.
Okay.
In other words, something has to happen.
Right, something's got to happen.
The third axiom is a bit more technical, but it basically deals with how we calculate probabilities when we have multiple events, particularly when we're dealing with infinitely many events.
Okay, I trust that the mathematicians have worked out the details on that one. So the axiomatic approach gives us a solid mathematical foundation for probability. But how do we actually assign those numerical probabilities to events?
Let's use a simple example, a dartboard. Imagine you throw a dart randomly at the board, which is divided into regions representing different scores.
So the sample space would be all the possible regions the dart could land in.
Exactly. Now, to assign probabilities, we look at the relative size of each region.
Okay.
If a region takes up a quarter of the board, we assign it a probability of 14.
So the bigger the region, the higher the probability. It's all about how much space an event takes up within the sample space.
That's the gist of it. The probability reflects the likelihood that the dart will land in a specific region, and we base that likelihood on the size of the region compared to the entire board.
That makes sense. It's like those carnival games where you try to toss a ring onto a bottle.
Yes.
The smaller the bottle opening, the lower your chances of winning.
Exactly. Now, once we have those basic probabilities in place, we can start exploring the tools and techniques for manipulating and calculating probabilities of more complex events.
Okay, I'm ready for the next level. What kind of probability wizardry awaits us?
Let's delve into what's called the calculus of probabilities.
Ooh, fancy.
It sounds fancy, but it's really just a set of properties and rules that help us calculate probabilities of combined events.
All right, let's open up that probability toolbox. What's the first tool we'll be using?
One of the most useful tools is the complement rule. It tells us that the probability of an event happening is 1 minus the probability of it not happening.
So if the probability of winning the lottery is 1 in 300 million, then the probability of not winning is 299,999,999 out of 300 million.
Exactly. It seems obvious, but the complement rule can be surprisingly helpful in simplifying probability calculations,
Right.
especially when dealing with complex events.
Okay, I can see how that would come in handy. What other tools are in our probability arsenal?
Well, we have properties like monotonicity,
Okay.
which basically says that if event A is a subset of event B, then the probability of A is less than or equal to the probability of B.
So if A is the event winning the lottery and B is the event buying a lottery ticket, then the probability of winning the lottery is less than or equal to the probability of buying a ticket.
Precisely. You have to buy a ticket to even have a chance of winning.
Right.
Another important property is subadditivity, which deals with the probabilities of unions of events. It tells us that the probability of A or B happening is less than or equal to the sum of their individual probabilities.
So the probability of getting heads or tails on a coin flip can't be more than the probability of heads plus the probability of tails.
That's right. It seems intuitive, but these properties form the backbone of many probability calculations. And as we encounter more complex scenarios, we need tools to handle situations where exact calculations might be tricky.
Okay, what happens when things get really complicated?
That's where inequalities like Boole's inequality and Bonferroni's inequality come in.
Okay.
They provide upper bounds for probabilities even when dealing with many events. Think of them as safety nets,
Okay.
giving us a maximum possible probability,
Yeah.
even if we can't calculate the exact value.
So instead of getting bogged down in complex calculations, we can use these inequalities to get a ballpark estimate.
Exactly. They're especially useful in fields like statistics and computer science, where you're often dealing with vast amounts of data and complex events.
All right, I'm starting to see the power and elegance of these probability properties. They give us a way to approach uncertainty in a systematic and logical way.
Absolutely. And now that we've explored these fundamental properties, let's dive into some specific techniques for solving probability problems.
Okay.
One of the most powerful tools in our arsenal is counting.
Counting. That sounds a bit too simple for something as sophisticated as probability.
Don't let the simplicity fool you.
Okay.
Counting techniques are crucial for determining the number of possible outcomes
Right.
in a given scenario,
Wow.
which is essential for calculating probabilities.
Okay, I'm intrigued. How does counting come into play in probability?
Let's take a classic example, the New York State Lottery.
Ooh, the lottery. Okay.
To figure out the probability of winning, we need to know how many possible winning combinations exist.
Right, we need to understand the size of that sample space of all possible lottery ticket combinations.
Exactly. And to do that, we need to consider whether order matters and whether we're sampling with or without replacement.
Okay, let's break that down.
Okay.
In the lottery, the order you pick your numbers doesn't matter.
Right.
A ticket with the numbers 1, 2, 3 is the same as a ticket with 3, 2, 1.
You're right. The order doesn't affect whether you win.
Right.
So we're dealing with an unordered sample.
Okay.
And since each number can only be drawn once, we're sampling without replacement.
Got it. Unordered without replacement.
Yes.
So how do we figure out how many possible combinations there are with those rules?
We can use a powerful tool called the fundamental theorem of counting.
Okay.
It essentially states that if we have a series of independent tasks,
Mm-hmm.
the total number of ways to complete the entire sequence is the product of the number of ways to complete each individual task.
Okay, so if I have 5 shirts, 3 pairs of pants, and 2 hats, I can create 5 times 3 times 2 or 30 different outfits.
You got it. The fundamental theorem of counting helps us systematically figure out the size of our sample space in a wide range of probability problems, including those tricky lottery odds.
Okay, so we use counting techniques to determine the size of the sample space, and then we can assign probabilities to specific events within that space.
Precisely. And to help us visualize those probabilities and how they're distributed,
Okay.
we can use a handy tool called a histogram.
Ah, histograms. Those bar graphs that show us the frequency of different values.
Exactly. Now imagine you take many random samples from a population and calculate the average of each sample.
So like taking groups of 10 students and calculating their average SAT score, we'd end up with a bunch of different average scores.
Right. And a histogram can show us the distribution of those sample averages, how often different average scores occur.
So it gives us a visual representation of how much those averages vary.
Precisely. The histogram provides a visual snapshot of the probability distribution of those sample averages.
That's really helpful. It's like we're connecting the abstract world of probability distributions to the tangible world of data.
Now, one of the most intriguing aspects of probability
Okay.
is how our understanding of events changes when we get new information.
Yeah.
This brings us to the concept of conditional probability.
Okay. Conditional probability. So this is all about how our beliefs are updated when we learn something new.
Exactly. It's the probability of an event happening, given that we already know another event has occurred.
Can you give me an example of this conditional probability in action?
Absolutely. Let's revisit the 3 prisoners problem.
All right, the prisoners.
Remember, we have 3 prisoners, A, B, and C,
Mm-hmm.
and one has been randomly selected for a pardon.
Okay.
Prisoner A asks the warden to name one of the other prisoners who will be executed,
Right.
hoping this information will improve his own chances.
Right. And the warden, following the rules, tells prisoner A that prisoner B will be executed.
Now, here's where it gets interesting.
Okay.
It seems like prisoner A's chances of being pardoned have increased from 13 to 12, right? After all, it's now down to him or prisoner C.
That's what I would think. It feels like the odds have shifted in his favor.
But that's not quite right.
Oh.
The key is that the warden's answer provides new information, and we need to update our assessment of prisoner A's chances based on this new knowledge.
So we have to factor in the fact that the warden couldn't reveal whether prisoner A was pardoned or not.
Yes,
His hands were tied.
precisely. The warden's response doesn't actually change the initial probability of 13 that prisoner A was pardoned. And to see this clearly, we can turn to Bayes' rule,
Okay.
a powerful tool for calculating conditional probabilities.
So Bayes' rule is like a probability update mechanism. It tells us how to adjust our beliefs in light of new evidence.
Exactly. It provides a systematic way to combine prior probabilities with new information to arrive at an updated, more accurate probability.
That's really helpful. It seems like conditional probability and Bayes' rule are essential for making sense of a world where new information is constantly coming our way.
Absolutely. And they have applications in fields ranging from medicine and finance to artificial intelligence and machine learning.
Wow, I'm starting to see how understanding probability can be a real superpower.
Now, another crucial concept that often trips people up, it's statistical independence.
Right. Independence is when one event doesn't affect the outcome of another.
Yes,
Like flipping a coin multiple times, each flip is independent of the previous ones.
exactly. But sometimes it can be tricky to determine whether events are truly independent.
Yeah.
Let's consider the scenario of rolling 2 dice.
Okay, 2 dice.
If we're interested in the event getting a sum of 8, we might mistakenly think the individual die rolls are dependent because we need a specific combination to get that sum.
Yeah, it seems like the outcome on one die would have to influence the outcome on the other to ensure we get that sum of 8.
However, it's important to remember that each individual die roll is still independent.
Okay.
The fact that we're interested in a particular combined outcome doesn't change the fundamental independence of the individual rolls.
Ah, so the constraint of a specific sum doesn't create dependence between the individual die rolls.
Precisely. It's crucial to distinguish between the independence of the individual events and the final combined outcome we're analyzing.
Got it. That clears up a common misconception about independence.
Now, as we delve deeper into probability, we need a way to transition from these abstract ideas of events and sample spaces
Okay.
to the world of numbers and data analysis.
Right.
That's where the concept of random variables comes in.
Random variables. Are we about to enter some advanced mathematical territory?
Not at all. Random variables are simply a way to assign numerical values to the outcomes of random events.
Okay.
Think of them as a bridge between the world of probability and the world of data.
Okay, so if we go back to our trusty coin toss example, we could assign the value 1 to heads and 0 to tails.
Exactly. That's a simple example of a random variable. It takes the outcomes of the coin toss, which are words, and maps them to numerical values.
So instead of saying the probability of getting heads, we can talk about the probability of the random variable taking on the value 1.
Precisely. This numerical representation opens up a whole new set of tools and techniques for analyzing and understanding random phenomena.
I'm starting to see how random variables bring a level of mathematical precision to probability. They allow us to quantify those random events and analyze them using the power of mathematics.
Exactly. And to characterize those random variables further,
Okay.
we need to understand their distribution functions.
Okay.
These functions provide a roadmap to the behavior of random variables, revealing the probabilities associated with different values.
Distribution functions. Those sound familiar from my statistics class, but I could definitely use a refresher. Where do we start?
Let's start with the cumulative distribution function,
Okay.
or CDF for short.
Okay, CDF.
The CDF of a random variable x,
Okay.
denoted as fx,
Okay.
gives us the probability that x takes on a value less than or equal to a specific value, x.
So if X represents SAT scores and F1400 equals 0.6, that means there's a 60% chance that a randomly selected student scored 1400 or lower.
Exactly. It gives us a cumulative picture of the probabilities up to a given point.
Hmm.
The CDF provides a comprehensive view of the probabilities across the entire range of possible values.
Okay, it's all about the probabilities accumulating as we move along that range.
Now, it's important to remember that we have different types of random variables. Discrete and continuous.
Okay.
For discrete variables, which take on distinct, separate values, we use a probability mass function, or PMF.
Okay.
This function gives us the probability of the variable taking on each specific value.
So for our die roll example, the PMF would assign a probability of 16 to each of the numbers 1 through 6.
Precisely. Each outcome has a distinct probability associated with it.
Okay.
Now, for continuous variables, which can take on any value within a given range, we use a probability density function, or PDF.
Okay, PDFs. Those are the ones that give us those smooth curves, right?
You got it. The PDF describes the relative likelihood of the variable taking on different values.
Okay.
It doesn't give us probabilities directly like the PMF does,
Right.
but rather the area under the curve of a PDF
Yeah.
over a specific interval represents the probability of the variable falling within that interval.
So the height of the curve at a particular point tells us something about how likely that value is.
Yes.
But to get the actual probability, we need to look at the area under the curve.
Exactly. And there's a whole world of different PDFs out there, each with its own unique shape and properties, describing a variety of continuous random variables.
This is making me think about all the different ways probability shows up in real life. like the distribution of heights in a population, the time it takes for a website to load, or the amount of rainfall in a given month, all of those would have their own unique probability distributions.
You're right. Probability is everywhere once you start looking for it.
Yeah.
And now that we have a grasp of random variables and their distributions, we can start exploring how to manipulate and analyze them even further.
Okay, I'm ready for the next level. What kind of mathematical maneuvers are we about to learn?
Let's delve into the world of transformations and expectations.
Ooh, transformations and expectations.
We'll learn how to create new, random variables from existing ones and explore powerful concepts like expected value and variance.
Transformations and expectations. It sounds like we're about to unlock some serious probability power.
Wow, so we've explored this incredible world of probability. We started with those, fundamental axioms
Yeah.
and explored a fascinating array of concepts from set theory
Yeah.
and axioms to random variables,
Uh-huh.
distribution functions, and even those more advanced techniques like moment generating functions.
Yeah.
It's amazing to see how these, seemingly abstract concepts
Right.
actually provide a framework for understanding so much of the world around us.
They really do. It's not just a theoretical exercise. It has
No.
practical applications
For sure.
in countless fields.
Absolutely. Speaking of practical applications, I'm curious to learn more about how those counting techniques we discussed earlier can be used in real-world scenarios. You mentioned the New York State lottery as an example.
Yeah, analyzing lottery data provides a great illustration of how counting principles can be applied.
Remember, to determine the probability of winning, we need to understand the size of that sample space.
Right, because the probability of winning is essentially the number of winning combinations divided by the total number of possible combinations.
Exactly. And to figure out the total number of combinations, we need to consider whether order matters
Yeah.
and whether we're sampling with or without replacement.
Okay, so in the lottery, we've already established that the order we pick the numbers doesn't matter, and once a number is drawn, it's not put back in. So we're dealing with an unordered sample
Right.
without replacement.
Precisely. And that's where the fundamental theorem of counting comes in handy. By breaking down the selection process into a series of independent tasks, we can systematically calculate the total number of possible combinations.
Right, we multiply the number of choices at each step.
Yeah.
So if there are, say, 50 numbers to choose from,
Yeah.
and we need to pick 6,
Right.
we'd have 50 choices for the first number, 49 for the second, and so on.
Exactly. And then we multiply those numbers together to get the total number of possible combinations.
Right.
It might seem like a simple calculation, but it's a powerful tool for understanding probabilities in scenarios like lotteries, or even things like calculating the odds of getting a particular hand in a card game.
Yeah, it's fascinating to see how something as, basic as counting
Right.
can unlock such complex probabilities.
It really is.
It's like we're using simple arithmetic to unravel the mysteries of chance.
Exactly.
Okay.
Now, shifting gears a bit, let's revisit another tool we discussed earlier, the histogram.
Okay, histograms.
Remember, histogram allows us to visualize the distribution of data.
Right, those bar graphs that show the frequencies of different values.
Yes. And it turns out it can also provide insights into the world of probability.
Okay, I'm curious to see how they connect to probability concepts.
Well, imagine we take multiple random samples from a population
Okay.
and calculate the average of each sample. For example, we could randomly select groups of 10 students
Yeah.
and calculate their average SAT score.
So we'd end up with a bunch of different average scores,
Wow.
each representing a different sample of students.
Exactly. Now, a histogram can be used to visualize the distribution of those sample averages. It shows us how often different average scores occur, giving us a sense of the variability in those averages.
So it gives us a visual representation of how much those sample means fluctuate.
Precisely. And what's fascinating is that the shape of this histogram can reveal a lot about the underlying probability distribution of the data.
So the histogram is like a window into the probability distribution itself.
Exactly. And as you delve deeper into statistics, you'll encounter concepts like the central limit theorem, which describes how the distribution of sample means tends to approach a normal distribution
Okay.
as the sample size increases, regardless of the shape of the original population distribution.
That sounds pretty mind-blowing. It's like we're uncovering hidden patterns and connections between data and probability.
It really is. And as you continue your probability journey, you'll find that these concepts and tools we've explored provide a powerful framework for understanding and analyzing data in a wide range of fields.
It's been an incredible deep dive. We started with the, fundamental building blocks of probability
It has been.
and explored a fascinating array of concepts from, you know, set theory and axioms to random variables, distribution functions, and even those advanced techniques like moment generating functions.
Absolutely. And as we've seen throughout this deep dive, probability isn't just a theoretical exercise. It has practical applications in countless fields.
It truly is amazing how a concept that might seem abstract at first glance has such profound and far-reaching implications in our lives and in the world around us.
Absolutely. Probability is woven into the fabric of our existence,
Yeah.
from the everyday decisions we make to the scientific discoveries that shape our understanding of the universe.
So as we wrap up this deep dive, I want to encourage our listeners to, keep exploring the world of probability. Look for those hidden patterns, those connections between chance and data, and see how probability is at play in your everyday life. Who knows what fascinating insights you might uncover?
And remember, this deep dive has only scratched the surface of a vast and fascinating subject. There's always more to learn and explore in the realm of probability and statistics.
Until next time, keep those minds curious and those probabilities calculated.